Hey everybody, Mr. D here checking in with a video on optimization. Optimization is basically the general term for either maximizing or minimizing a particular construct. So in doing that, what we need is a function which serves that objective. So we call that the objective function. Sometimes that objective function will have one variable only, and that will work very well. Other times we'll have an objective function that we create, but it'll have two variables in it, and we'll have to somehow find a way with other information in the question to distill it down so that way we have just one variable. Because ultimately what we want to find is when the objective function's first derivative is equal to 0. And those of you taking high school calculus know that we are only able to do derivatives when there's one variable, typically x or w or whatever the variable of integration or of derivative differentiation is. And you'll see what I mean by this coming example. So I'll allow you to just have a quick look at this question. We'll focus on part A. You can pause the video and just read this question. Welcome back. You've noticed that the important information here is the volume is set. It has to be 24 pi centimeters cubed. And we need h in terms of r. So essentially what we need is h as a function of r. Well, how do we do that? Well, there's some information that was given. So we know that volume is equal to 24 pi centimeters cubed. You may not recall the formula for a volume of a cylinder. I mean, it's easy to look up online, or if you have a formula booklet ahead of you, if you're an IB student or an AP student, you can leverage the prior learning section of those formula booklets. But for volume, it's pi r squared times h. So pi radius squared, that's the area of the base, times stacking it up h times. And that's equal to 24 pi, given in the question. What we need to do is divide both sides by pi r squared. So what we're going to do, because ultimately what we want to do is have h as a function of r, and we can't have r's on this side. So we're going to divide both sides by pi r squared. And you'll notice that this is a fancy version of 1. Right here, this right here, divided by itself. That's just a fancy version of 1. Same thing here with pi. Pi divided by pi is basically another fancy version of 1. So what that allows us to do now is to come up with the expression h equals 24 over r squared, final answer. Or alternatively, you can write that as 24r to the negative 2. So that's h in terms of r. Moving on now. The material for the base and the top of the can costs 15 cents per centimeter squared. So in this case here, the base and the top, that is 15 cents per centimeter squared. But the side, the curved side, so this side here, which is curved, it's 10 cents per centimeter squared. Show that the cost function C in cents is that expression there. So the prices for the area. So let's break the area up into pieces. We have the area of the basin, area of the top. They're both circles, and the area of a circle is pi r squared. And then from there, From there, what we need to do is multiply it by 2, because there's 2 of them. And then also we have to multiply it by the cost per centimeter squared, which is 15. And that's going to be our base and the top cost function. But we also have the problem of the curved side. So the curved side, if you were to just slice it across from top to bottom, like slice that from top to bottom, it would end up in flattening it out. It would look something like this. It would look like a rectangle, and then you'd have the circle for the top, and then the circle for the base. That's the material you need. So the height, that's basically would be the width of the rectangle. But the length of the rectangle, that's the part that is a little trickier. But if you were to unravel all of this, so in other words, if you were to cut that circle and then bend and flatten that circle, we basically would end up with the circumference of the circle. In other words, the perimeter of the circle, which is 2 pi r. So that would be the width. So length would be the height, width would be 2 pi r. So now we have length times width, which would be 2 pi r h. 2 pi r times h, length times width. Well, it kind of looks like right now we have 30 pi r squared, which is what we need. So that's kind of nice, right? We have that right now, 30 pi r squared. So we're done with that first term. The second term, not so much. We have a little bit of work to do. But if we go back to part A, remember h is equal to a function of r, 24r to the negative 2. So what we're going to do is we're going to write down 24, I think it was 24 pi, I believe. No, it wasn't. It was just 24. 24r to the negative 2. It's better to double check these kind of things. And we're going to multiply that by 2 pi r. Again, we don't want to change that first term because it's already in the show that view. The next one, we have to get into the 480 pi over r view, or that form. So we're going to multiply the coefficients where we get 2 times 24. But I've also, one thing that we have to consider is the cost, which we haven't done yet before we get carried away. Notice how initially here, we looked at the cost as 15 cents. We haven't multiplied this, the side, by its cost per centimeter squared. So we're going to multiply that. Let's just do that before we forget. We're going to multiply that by 10. So basically that's going to end up being, let's see if I can maybe just tidy that up just a little bit. There we go. Make a little space there for us. So 24 r to the negative 2 times 10. There you go. So now we can simplify all the numerical coefficients. So it's just 2 times 24, which is 48, times 10, we get the 480. Let's not forget the pi. And then we have r to the 1 times r to the negative 2. We can write that r to the negative 2 as 1 over r squared. So why don't we do that? So we'll leave the r as it is, but we're going to divide by r squared, which is basically the r to the negative 2. Now we can simplify that, and we have an expression in r, which is a function in r, 30 pi r squared, that's the cost for the top and the bottom, plus 480 pi over r as required. So now we have that second term. Very good. Now, moving ahead. Given that there's a minimum value for c, find the minimum value in terms of pi. So whenever you see something like optimizing, which is minimizing or maximizing, that implies derivative. Set to 0. When is the tangent line horizontal? So in other words, if we had a function like this for cx, or for cr in this case, so if we called this c, we'd want to know for the minimum, when is the tangent line horizontal? When is the derivative equal to 0? That implies the tangent line is horizontal. If there were a maximum question here too, it would be the same thing. It would be the first derivative equal to 0. It doesn't matter. Every single type of optimization question is a C prime R or F prime equal to 0. So let's go back and retrieve our cost function, which is 30 pi r squared. So remember, C equals 30 pi r squared plus 480 pi. And then we had the r underneath, but we're going to bring it up and go r to the negative 1. So we can do the derivative a little more efficiently. So C prime R, so it's just a function of R. You don't even need to write the R, but just for form purposes, I'm including it there. We'd get 2 times 30, so 60 pi R, plus negative 1 times 480, so it's negative 480 pi. And then again, subtract 1 from negative 1, so negative 1 minus 1, which is negative 2. So let's just tidy that up a little bit. And then we have to set that equal to 0. I always try to common factor. If there's a possibility of common factor, let's try to do that. It would simplify the expression a little bit. We have a 60 and a 480 coefficient. I know that 6 goes into 48 8 times, so that means 60 would go into 480 8 times. So it would be 60. We have a common pi, so let's do 60 pi. And then r minus, I said that was 8 times r negative 2 equals 0. We're going to divide both sides by 60 pi, and we're going to be left with r minus 8. We're going to write the r squared downstairs equals 0. And then multiply both sides by r squared to clear fractions. So when you do the distributive property, you're going to be left with r cubed minus 8, because the r squareds divide out, equals 0 times r squared. Basically, 0 times anything is going to be just 0. So, so in this case here, well, 0 times r squared is just going to be 0. So we're left with r cubed equals 8. And then we have to take the cube root of both sides, and therefore r is equal to 2. That's the radius. That's going to provide a minimum cost, yet still having the 24 pi volume. What's the minimum value in terms of pi? Well, we didn't find the minimum value yet. We have to substitute this value into C. So we're going to substitute this to find the minimum value of the cost for C. So C at 2 equals 30 pi times 2 plus 480 pi r to the negative 1, which will just be r down here. So that's 60 pi, 2 goes into 480, 240, and each of those are pi terms. So let's make some room there. I omitted the pi. I have to make sure we're a little more careful than that. It's 60 pi plus 24, 240 pi. So we're left with 300 pi, the cost that's minimized in cents.